Okay, so we talked about how you can standardize any random variable and turn it into something that has mean 0 and standard deviation of 1. So the standard normal is that normal random variable. And we almost always use z to denote a standard normal random variable. I think I used that in the last video as well. Okay, so z is distributed normally with a mean of 0, standard deviation, or variance of 1. They're both 1 there. Other notation that is almost ubiquitous is to write the PDF of z as lowercase phi of x. Okay, so that would be our normal over root 2 pi. I usually have a sigma down here in this denominator, but my sigma is 1 times e to the negative. It would normally be negative x minus mu squared because mu is 0. It's just negative x squared divided by, normally it would be 2 sigma squared, but that's also 1. So the PDF looks a little bit simpler. So root 2 pi. And again, the PDF has this lowercase phi, and the CDF is then an uppercase phi that looks like this, and that is just the integral of dx. All right. The standard normal, this PDF is what we find the integrals of the cumulative probabilities for in tables. So I've got a little part of a table that's in Bertsekis and Sissequis. It's on page 155. Just about any statistics or probability book will have a table of normal probabilities, of cumulative normal probabilities. There's one in Wikipedia. They're easy to find. And the way to read these tables, they do give us cumulative probabilities. And so if we want something like phi, the CDF of a standard normal random variable for 0.25. Okay, so we'd be asking what is the probability that that normal random variable with mean 0 and standard deviation 1, z, is less than or equal to 0.25. Okay. So drawing that, there's standard normal here, and what we're looking for is, so the mean here is at the highest point, the mean is 0, and we're asking what's the probability that z is less than 0.25, and that would be this whole area, everything under the curve to the left of 0.25. That's the probability. Again, we can't find a nice closed form integral for the normal PDF, but they can be computed by hand and we can just read it off the table. Okay, so to read it off the table, we're looking for the probability that x is less than 0.25, and the table is just really simple. It's organized in terms of tenths here and hundredths. So if we want the probability that z is less than 0.25 here, we're going to go down to 0.2, and then we're going to go over to the 0.5. Okay, so we're getting the value that we're looking for is equal to the sum of the 10th place on the rows and the 100th place on the column. And this right here, this is the number we're looking for. Okay. that equals 0.5987. That is indeed the probability that standard normal is less than 0.25. Okay, good. So far, so good. Kind of cookbooky, but useful. The final thing I want to do is what if it's not a standard normal? Okay, what if we have some other normal random variable? We're not always, when we're using normal random variables to understand our data, the mean and the variance might be very different from 0 and 1. It's no problem, because any question about a regular normal probability, regardless of the mean or variance, can be turned into an equivalent question about a standard normal. Okay, so to I want to go to another screen. Yeah, I think rather than writing all over this, I'll add one more board here. So let's look at one last example here, and let's say that we have x is normal and it has mu 25, so mean of 25 and standard deviation of 10. Okay, so it is standard deviation, meaning that the variance is 100. When I put in a standard deviation, I don't need to take the square root here. I've already done that. So I've got this normal random variable, and what I want is the probability that x is less than or equal to 30. My table here is just about z. It has mean mu and standard deviation of 1. I'll write this more nicely here. 0. Mu is 0, sigma is 1 here. But this question about the non-standard normal is the equivalent of a question about the standard normal. Okay, so what I want to do is transform the question about the mean of 25 and the standard deviation of 10 into something that would have a mean of 0 and standard deviation of 1. Okay, so let's just draw the pictures there. So this picture is, I'll use black for my version of I. So its mean here is 30. And what we, oh sorry, its mean is 25. 30 is the value we're looking for. So its mean is 25, and we're looking for the probability that's less than 30. And what we want to know then is what's the equivalent probability over here with the standard normal, where the mean is 0. There's some other number here that's going to have the same probability below it as the x that we started with has below 30. So what we want to know is what's this equivalent number for the standard normal. And we get that by just applying the same transformation to this question that we would apply to x to get to z. So check it out. So this probability that x is less than or equal to 30 is the same as the probability that x minus 25 divided by 10 is less than 30 minus 25 divided by 10. See what I'm doing? I'm just performing the same operations on my 30 that I am on my x. I'm doing the same thing on both sides of my inequality. That is totally legit. And what do I do when I get that? Okay, well now this is Z. I just standardized X. I just subtracted off its mean and divided the result by the standard deviation. So I transformed this part of the question into Z. And this part is just a number. What number is it? 30 minus 25 is 5. Divided by 10, it is the probability that Z is less than 0.5. And that, because it's a question about Z, we can look up in the table. It's not, that's lame. I cut off the table before I should have, but I'm actually looking at the book, and I can tell you that the very next line here, 0.5, has 0.6915 right here in the place where we want it, where there is a 5 in the tenths column, there's a 0 in the hundredths, and that is the value that we're looking for. Okay, so that's how we find the cumulative normal probabilities. And you're thinking, that's really how we find it. In a sense, it is. The way you find cumulative normal probabilities, if you actually need them, is you type it into a spreadsheet, you ask R. This table lookup process is something that is, by and large, automated, and that is mostly what you are going to do. On the other hand, just even across statistics packages, they do it a little bit differently. You kind of have to know what the computer is doing to know what to ask it. So going through this process a couple of times will help you understand how we're getting those probabilities. We're going to do a couple more examples in the workshop of that. So that's where we're going.